You ready, Dylan? Excellent. Work. This next unit is on work, energy, and power, and some associated concepts that go with it. Energy in particular, work in particular, are fundamental concepts to our understanding of the universe. But the problem is they're also words in English that have meanings different from physics. So work in physics means something very specific. Work in English, I'm doing work. You mean you're getting sweaty, you're getting tired. Work is not tiredness. Work is, well, let's talk about it. First of all, work is a scalar. It's defined as the product of the force component in the direction of the motion and the distance moved. It's defined as force times distance, but your force and your distance must be in the same direction. Units, well, Newton meter, but we call that a joule, symbol capital J. So let's start to apply this already. How much work does Ethan do when lifting a 50 kilogram mass to a height of 5 meters? Which Ethan? Let's pick on this Ethan. We'll make it you. Okay. Underline the word lifting. That's very important. I would say, Paula, what's this question asked me to find? Work. So I would say, well, work is force times distance. Ethan, when you lift something, what force are you doing work against? Gravity. And is gravity in the same direction as the height that you're lifting? Say yes. Yeah. So we can use work equals force times distance. It's going to be the force of gravity. If you want to, you could put a little FG in your equation. Or you could say, you know what? That's mg. And you might recall last year I often called a vertical distance a height. How much work will Ethan do lifting this? 50 times 9.8 times 5. Which is going to be 980 times 25. That's the same as going times by 100, 9,800, and dividing by 2 twice. 4,900, 2,450? Double check me. Yes? Joules. Is that a lot of work? Well, honestly, it depends how fast you do the work. First of all, lifting 50 kilograms, that's about 120 pounds. Lifting that up 5 meters, that's about 1.5 stories. You'd be basically piggybacking. You know what? It'd almost be like piggybacking somebody up those stairs and then another half set of stairs. It'd be tiring, but it's not how much work you do, it's how fast you do the work. If I gave you 2 hours to piggyback that person, you could pull it off no sweat. You'd do one step every 5 minutes and relax. Suppose Ethan is unable to lift the mass straight up. He doesn't have the strength. Instead, he decides to push the mass up a ramp at an angle of 30 degrees. Here's our ramp with an angle of 30 degrees. Now he's going to end up at the same height, so h is still going to be 5 meters. But instead of just brute force lifting it straight up, he's going to push the mass up a frictionless ramp. I'm going to draw the mass as though he's gone partway up. I'll put it right there. If he ends up at the same height, how much work will he do if we assume there's no friction? Well, how did we just define work? Work equals what times what? So let's write that down. Which distance? This time, Kareem, that distance. Yes? Okay. Which force? The force in that direction. You know what? Let's label the forces on this block. Kareem, what are the forces acting on this block? Get the obvious one. Is mg in the same direction as that distance? Say no. Huh? Whose phone was that? Came from over here. Mina, was it your phone? Better put it off. And put your phone away, please, face down. Thank you. You're lucky this isn't your class, otherwise you'd be owing us all Timbits. You know what I should do with that gravity force? Well, hey, hopefully it's a habit now. What should I do with that mg straight down when I'm on a ramp? Well, let's break it into components. So I have mg perpendicular, I have mg parallel, and there would also be a normal force. Hey, which force is in the same direction as the motion? Do you see it? It's not mg. What? Mg parallel. You okay with that? So I'm going to modify our equation. It's going to be which force? Mg parallel times distance. What was mg parallel? What was our dumb shortcut that we'd memorized for 2 lines? Okay, so I'd like you to write this. W equals mg sine theta, but don't write the distance yet. Just leave us. We're going to come back to that. Okay? I'll draw a blank. Don't draw a blank there, but we're going to put that in there. Okay? Distance. How can I figure out how long this... Well, first of all, what part of the triangle is this? Opposite, adjacent, or hypotenuse? I'll put a little h right there. What about the height that I know, that 5, opposite or adjacent? Which trig function? Yep, I'm going to get the sine of the angle is 5. You know what? Let's even call it the height. I'll put an h in there for height over the distance. I know h for hypotenuse and h for height, so we're running out of letters here, but the h in there is not hypotenuse, the h in there is height. I want to get the d by itself. How would I get the d by itself? Okay, d is equal to the height times the sine of theta. Is that okay? So I'm going to plug that into here. D is equal to, sorry, not the height times the sine of theta. You're going to times the d over and divide by sine. Yes? I said that totally wrong. D is equal to h over the sine of theta. Is that okay, right? The d would get multiplied to there, and the sine would get divided over to there. Is that okay, Ethan? This is your question. Yeah? So if I plug that in, I'll get h so I get that mg parallel is mg sine, but I get the length of the ramp is the height divided by sine. What happens? What do you see here? Eric, you're right, loud and proud. What? Hey. In fact, we end up again with mgh. This is why work and energy are scalars. They don't care about the path that you took to get there. You still get the easier version of the equation, mgh. And we would still end up doing 2,450 joules of work. Now, if you're pushing it up the ramp, Ethan, the force you would have to apply, mg parallel, would be smaller, but your distance would be correspondingly larger. We call this a simple machine. A ramp is an example of a simple machine. What does a simple machine do? It reduces the force at the expense of increasing the distance, because we're still stuck with doing the same amount of work. It reduces the amount of force, but the trade-off is it increases the distance. There are 3 main simple machines that humanity has had for about 2,000, well actually for about 4,000 years. The ramp, the lever, and the pulley. All of them basically do the same thing. They reduce how much force you need to apply, but you're going to need to apply the force for longer, a bigger distance. Okay? The amount of work remains the same. In fact, the reason, Kareem, that you and I did this algebraically was to show you, yeah, the sine thetas cancel and you get mgh. Yeah? Okay. Oh, let's make it more realistic. If there's friction on the ramp, You would have a tiny force this way, which means your net force goes down a tiny bit. You end up doing slightly more work, but you know what? The force is still significantly smaller than lifting the object directly. As far as we know, the Egyptians built the pyramids without wheels, but using ramps. That was enough to reduce the amount of force required to get those massive blocks up to the pyramids. They still do the same amount of work, still MGH. The aliens built the pyramids. Actually, it's a lovely calculus question. You can show that if you calculate the work, it's a calculus because it's a changing, you got a slant in there, you got a changing height and a changing speed. Anyways, you can show it's perfectly feasible in about 20 years for X number of laborers to do that much work and get the pyramids built. And it turns out it took them about 20 to 30 years to build each one, so it fits out quite nicely. No aliens required. Example 3. Suppose we have a ball at the end of a string, like this, and it's rotating at a constant speed. It's rotating at a constant speed because I'm exerting a constant force. Well, the string is exerting a constant force on the ball. How much work is done on the ball by this force? Now, I'm talking about right now while it's going at a constant speed. I'm not talking about while it's slowing down or speeding up. Okay? Well, what direction is the force in this question? It says so in the question, and it says so in the picture. What direction is the force in this question? It says so in the question, and it says so in the picture. What? The force is towards the center, but the direction of motion is this way. Are the force and the distance in the same direction? You're doing 0 joules of work. In other words, if I'm spinning that ball at a constant speed, it is neither gaining nor losing energy. Its energy state is constant. Okay? The force and the distance have to be in the same direction. In general, a force in exactly the same direction of motion, like F1 below, does positive work. A force in the opposite direction of motion, like F2 below, does negative work. Really, we would say this: the object gains energy if you apply a force in the opposite direction. The object loses energy. So, Courtney, work can be negative or positive, but it's not a vector. It's unlike in Unit 1 when we said negative 9.8 meant down and positive meant up. Here, a negative doesn't tell you a direction. A negative tells you you lost energy. A positive amount of work tells you you gained energy. It's a scalar quantity. Mr. Dulac, what a deem. What if the force and the distance aren't in the same direction? Like here, a child is pulling a wagon along the driveway, exerting a force F along the handle of the wagon. How would you calculate the work done by the child on the wagon? Well, here's the force F. If you want to, you can call it F applied. Is it at an angle? Then hopefully I've conditioned a reflex into you now. Loud and proud. Okay. So let's break it up into Fx and Fy, where there is our angle theta. Now, looking at the picture, this is the distance. Looking at the picture, the distance is in that direction. Which of those 3 components on the triangle is in the same direction as the distance? The x component. So a better version of force would be Fx times distance. Sorry, a better version of work, I said of force. A better version of work would be Fx times distance. Although, let's do a bit of trig. Fx, opposite, adjacent, or hypotenuse? Adjacent. What about F applied? Hypotenuse. So I have adjacent, I have a hypotenuse. Which trig function? Which trig function? We would go cosine of theta equals fx over applied. Marcus, how would I get the fx by itself? What would I do with the f applied? Okay, so here is our new and improved definition of work. It's really the applied force times d, but you would have a cosine multiplied in. And really, this is the more universal force equation. It's F times D cos theta. That one's not on your formula sheet because to derive the component isn't that tough. What if the force and the distance are in the same direction? What if theta is 0 degrees? What's the cosine of 0 on your calculator? 1. Oh, and you just force times distance. What if they're in opposite directions? So theta is 180 degrees. What's the cosine of 180 on your calculator? Negative 1. That's why I said if you go in the opposite direction, you're losing energy. Negative work. What about if they're at 90 degrees, like this circle example? What's the cosine of 90? 0, which means a normal force will never do work. Because normal forces, by definition, had to be at 90 degrees to whatever surface they were on. Okay? So some good consequences comes out of there. But having said that, Courtney, the only reason I'm doing this derivation is to show you it's kind of cool that you get a positive, a negative, or 0. But you don't need to actually, it's not on your formula sheet. Okay? What if the force isn't constant? What if the force is changing? Well, we're going to end up with 3 definitions of work. The first one is on your formula sheet, work equals force times distance. The second one is not on your formula sheet, but later on in this unit, I'll give you a dumb, clever way to remember it. Work is also the area underneath a force versus distance graph. Matt, what kind of a graph is this? What's on the y-axis? What's on the x-axis? What's my force initially? 1 Newton. And what's my final force, assuming that I did these properly? 3. I was kind of eyeballing it, but it's a vague graph. So is the force changing? Yeah. So we cannot go force times distance. The most common mistake is I will be giving you a graph on your next test, not this one, not your forces test, but your next one. I give the kids the graph and they say, 18 joules. They go 3 times 6. No. I'll tell you what it is. Oh, A asks, how much work is done moving this object from 2 meters to 6 meters? I'll tell you what the answer is going to be. That area. That area. What do we call that shape which has 2 sides that are parallel and 2 sides that aren't? It's an obscure shape. It begins with letter T. It's a trapezoid. It's a trapezoid. I always ask, does anybody know the equation for the area of a trapezoid? Eric, did you know it last year? I'm trying to remember. You know what? It's obscure and it's redundant and unnecessary. I don't even have it up here. I derive it every time. I think it's 1/2 times bracket A plus B close bracket times the height, something like that. You know what? The reason we don't teach it, the reason I don't make you memorize it, the reason none of you really know it is because you don't need it. Any trapezoid can also be broken up into a triangle and a rectangle, like that. I'm going to call this bottom area, area 1, and I'm going to call this top area, area 2. Those are bad colors. I'm going to erase the highlighter. Now you can see better. On my screen, it looked nice and dark, but I realized in the projector they kind of blended too much. Okay? Now, if I want to find the work, it's going to be the area of the first part plus the area of the second part. What is that first shape? It's a rectangle. How do I calculate the area of a rectangle? This I will expect you to know. What's the equation for the area of a rectangle? You can call it base times height, or you can call it length times width, regardless. So it's going to end up being 4 times 2, from 2 to 6 is 4, and 2 high. Psst. What's the area of a triangle? Now, some of you are going, I can't remember. Believe it or not, it actually is on your formula sheet. On the same page where it has the quadratic equation, it's the page where I shrunk things down 2 to a page. It's got a bunch of math stuff on the bottom right area there. I think it does say either half times base times height, or it says base times height divided by 2. I can't remember which version you got. Yeah, I always go with base times height divided by 2, because why use a half when you can divide by 2? So this triangle has a base of 4, a height of 1 from 2 to 3, divided by 2. You know what? This is 8 plus 2. I can do that in my head. How many joules of work did it take? 10 joules. The object gained 10 joules of energy. Probably kinetic energy. It probably sped up. Oh, I don't know. Could have been lifting it up. I don't know. Could have gained potential energy. Okay. So work is force times distance. If they give me a graph, work is the area under a force versus distance graph. Usually if they give me a graph, it's because the force is changing. Energy. Energy is the ability to do work, the ability to exert a force over a distance. There are many forms of energy. There's the energy of motion, which we call kinetic. There's heat energy created by friction. There's gravitational potential energy. This is the amount of energy an object has because of its height or location. There's chemical potential energy. By the way, potential energy just means stored energy. There's many types of stored energy. Gunpowder, the food that you eat, has chemical potential energy in it. Other forms of energy, sound is a form of energy. Elastic energy, the energy stored in an elastic band when you pull it. Nuclear energy, the energy stored in the nucleus of an atom. There are many, many types of energy. We're going to end up looking at 2 main types. Well, 3 if we include heat. Sometimes when we do work, we make things move. When you apply a force over a distance, sometimes it causes the object to move. Fill in the proof below to find an expression for motion energy. Okay. Well, let's see. It says definition of work. The definition of work equals force times distance. But I can break force down. F equals what? MA. I can write this as MA distance. Okay. And then I'm going to get clever here. I'm going to multiply the front by a half, and I'm going to multiply the D by 2. If I times by a half and I times by 2, what have I really multiplied by? Think about it. 1. So have I changed it? No, I'm making the answer look different. And the reason I did that is if I use VF squared equals VI squared plus 2AD, I can get the 2D by itself, which I have sitting right here. 2D is going to be VF squared minus VI squared all over A. Yes? And if I plug that in there will be an A there and an A there, but they'll cancel. The 1/2 drops down, the M drops down. Oh, and if VI is 0, if we start at rest, I get a half mv squared. Remember that from last year? There it is. There's the derivation of how you can calculate kinetic energy as an equation. Kinetic energy is equal to 1/2 mv squared. Is that on your formula sheet?
Yes.
Sort of. There's a bit of a problem. On your formula sheet, they're going to use E with a subscripted K for kinetic energy, and they're going to use E with a subscripted P for potential energy. And I know why they do that. It's technically, well, It's also wrong. In physics, the correct letter to use for energy is a capital U. Why? Because Latin. I should not use two capital letters for one variable. That's just bad math. But I'm going to do that on purpose because later on, there's going to be a unit that has a capital E, which means something totally different from a capital EP or a capital EK. So I'm trying to do this to avoid confusion later on. But Sarah, I am technically wrong. I shouldn't use KE for kinetic energy and PE for potential energy. So you have to translate your sheet a little bit. Try and give you some numbers. The amount of energy in a jelly donut is about 10 to the 6th joules. There's a very small amount of energy. It's called an erg. Shows up in atomic physics. And it's about the same amount of energy as one mosquito push-up, or 10 to negative 7 joules. So here's our first thought experiment. A golfer wishes to improve his driving distance. What would have more effect? Doubling the mass of his golf club, or doubling the speed with which the club strikes the ball? Convince me. I want to improve my driving distance. What would be better? Using a heavier club, doubling the mass, or swinging twice as fast with the same mass? Yeah. First, what's your answer, A or B? B? Why? Yeah. So, V squared, so 4 times the energy. This is why, Dylan, over the past, 30 or 40 years, sports equipment, most of it has become lighter. And any sport where you strike something, it's a trade-off because mass does also add energy, but if I make the equipment lighter, if I can get more speed, I'm getting that increase squared of energy transfer. So baseball bats, hockey sticks. Well, baseball bats are very regulation, actually. That one I can't say they've made lighter. That's regulated. But all the composite hockey sticks, both flexible and lighter. Tennis rackets have become far lighter, far lighter. It's a trade-off. But hey, the faster we can swing, we get the squared. This is also why in a car accident, if you're going twice as fast, 4 times more damage. Or to use real speeds, if you're in a car accident at 20 kilometers per hour versus 80 kilometers per hour, 80 divided by 20 is 4 squared, 16 times more damage at 80 kilometers per hour. Not 4 times more damage, 16 times more damage. So slow down and don't drive dumb. Next page. I was going to walk you through the derivation of potential energy, but we already did when we looked at Ethan carrying something. He said, look, Mr. Dewick, the force is gravity. It's mg. So you know what? Gravitational potential energy is just mgh. We already kind of derived it earlier. It's the force of gravity times the distance that you move it through. That one is also on your formula sheet. Usually we focus in this unit on mechanical energy, which has 2 main types, kinetic energy and stored potential energy, usually because of gravity, but not always. And now we come to the WorkEnergy Theorem. This is our third definition of work. Work is force times distance, yes. Work is the area under a force versus distance graph, yes. But work is also equal to the change in potential plus the change in kinetic. And I want, is that you being a meathead, guys? Cut it out, please. Yeah, but don't do that. You're interrupting my lesson. I want all of you to get out your yellow formula sheet right now, and you're going to add this equation. This is the only time you're allowed to add an equation to your yellow formula sheet. So if you go to your yellow formula sheet, and you find the work, energy, and power section, which is right there, you can write work equals change in potential plus change in kinetic. You can also add it to your blue sheet if you want to, but you definitely want to add it to your yellow sheet. Work is equal to the change in potential plus the change in kinetic. You're the first group that I'm not making memorize this one. I'm letting you put it on your formula sheet. You're welcome. Oh, if you're on a flat level surface like a road and your height isn't changing, then the change in potential is 0. So you'll see some textbooks give you the work-energy theorem as just the change in kinetic. I'm not wild about that. I'll include it because it shows up sometimes. But to me, no. The work done on an object, it's its change in stored energy plus its change in motion energy. Put your pencils down, look up. I showed this last year, but a couple more, we're done. A couple more, we're done. Natalie, what's example 8 asking me to find? How much work? So here's what don't write this down. Nat, here's how my brain works, no pun intended. Don't write this down. The first thing I think is, well, work equals force, don't write this down, times distance. Read the question. Do you see a force or a distance in the question? You see a force in newtons and a distance in meters in the question? You see a force in newtons and a distance in meters in the question. Say no. No. And I don't see an easy way to find any of those. Like if there was a mass and an acceleration, I'd say, that's a force. I don't see that. I see a mass but no acceleration. I'm going to ask you again. My first thought, Nat, is I'll try force times distance. Do you see a force or a distance in the question anywhere? Loud and proud. My second definition of work is the area under a force versus, don't write this down, distance graph. Did they give you a graph? Say no. So pick your pen up or your pencil up, Nat. My third definition of work, write this down, is that it's the change in potential plus the change in kinetic. This is the one that we just put on our yellow sheet. Probably the most flexible definition of work, although it's a bit of a pain. Now, Nat, the change in potential would be because there was a change in height. Do you see a change in height anywhere in the question, implied at all? No, so I'm going to assume the road's level. So I have change in kinetic. What's change in anything? Final minus initial. So the work is going to be KE final minus KE initial. Are any of those 0? It says we're coming to a stop, so that's going to be 0. So I'm going to get the work is equal to negative a half mv initial squared. What's the negative telling me? There's 2 ways to think about it. Number 1, the object is losing energy. Or number 2, the force that's applied is going to be in the opposite direction of the distance. If this car is moving north, the force has to be south. If this car is moving forward, the force has to be backward. I'm going to get negative 0.5, 1200, 32 squared. Negative 0.5 times 1200 times 32 squared. And I get, I'll write this one in scientific notation, negative 6.14 times 10 to the 5th joules. What's the negative telling me? That I lost energy. You will often see in the final answer in the homework or on a test, they ditch the negative because they don't care, that they just want to know how much work was done, and you could say, oh, well, you did that much work. It can be, in that sense, positive. But the car had to lose that much energy. Something else had to gain that much energy. Last one, example 9. Hedrick, what's example 9 want me to find?
The minimum amount of work.
Work. Minimum amount, because I'm ignoring friction and other things. At first, I thought force times distance, but I also noticed there is a speed in there, yes?
Yeah.
Why don't I use the one that has both? I'm going to use my more flexible definition of work. Work is the change in potential plus the change in kinetic energies. Hedrick, what's changed in anything?
Final mass.
So this is going to be PE final minus PE initial plus KE final minus KE initial. You don't have to put the brackets there. I'll just put them so you can see where the terms came from. Now, our potential energy is the energy due to the object's height. Hedrick, are any of these 0? What's our final height?
245.
That's not 0. What's our initial height? What's a reasonable assumption?
0.
Let's assume we started on the ground. Okay. What about kinetic energy? What's our final speed?
95.
What's our initial speed? Let's assume before we pull the trigger that the cannonball was at
0.
Okay. Okay. By the way, that's why I'm also saying minimum. There would be other types of energy. There would have been sound energy that was exploded, and that would have had to come from somewhere. There probably would have been a lot of heat generated. That would have had to come from somewhere. So this is the minimum amount of work that the cannon did. Oh, and we're totally ignoring air resistance and air friction, which would also bleed off a lot of energy. Is that okay? So Hedrick, I'm going to get mgh final plus a half mv final squared. Here we go. The mass, 19, g, 9.8, final height, 245 meters, plus the 0.5, the mass, 19, 95 squared. I'm going to assume a reasonably big number because it's a cannon. And I get, you get 131356.5? Someone double check me. Yeah? To 3 sig figs, 1.31 times 10 to the 5th joules. That's how much energy the cannonball gained, 'cause it's positive. Actually, probably gained more than that, but that's it gained at least that much. What's your homework? Well, your homework is to, for the remainder of class, work on your ultimate study guide review. But for next week, Monday, because I don't see you for a week, questions that you're capable of doing. Here's what I assigned my block A's. One, two, 4, 6. Number 6, by the way, is a repeat of the ramp question that Ethan and I did, where it's having you figure out the force to go up the ramp, and then when you, the work to go up the ramp, and when you go MGH, you'll get the same answer. So what did I say? 1, 2, 4, 6, 7, 8, 9, 12. 8, 9, 10, 12. 13, 14, 15. So, Adim, you want to read that back to me? It was 1, 2, 4, 6, 7, 8, 10, 12, 9. Okay. Thank you, sir.